All right, for people who are joining this live stream, we are going to talk about modeling, or more specifically, metamodeling. And so here's the basic concept. There are models that people use to describe things. They might be a random walk. They might be diffusion. They might be diffusion limited aggregation. They might be a self-avoiding random walk. They might be an agent-based model of some kind. They might be Boids. They might be lots of kinds of things. Or they might be cellular automata or differential equations or other kinds of things. We have good frameworks for representing models that are based on systems of ordinary differential equations, partial differential equations, etc. But we realize that although many people have implemented these things many times in Wolfram language, we don't have standardized frameworks for implementing things like agent-based models. And perhaps as a way to kind of get a start in understanding that, we could look at our demonstrations project and look for, let's see, we have a section called models. Here we go, models. And we have models, there we go. Do you think multi-agent, see this is a good, actually, let's take this as a sample of what kinds of things we're talking about here. For example, if we look down this list, many of the things that are here, we have good frameworks for dealing with modeling, random processes, substitution systems, trees, discrete models of various kinds, cellular automata, and so on. This one is sort of a holdout. So let's take a look at this and see what we can understand about this. So, for instance, if we look at something like this, can somebody characterize what is really going on in a system like this? Christopher, perhaps.
I mean, I don't know exactly what this one is doing, but I mean, I guess it's the way you normally implement something like this is that, you have a bunch of agents, and maybe they have different parameters or different types and so on. And there's some piece of code that runs in all of the agents.
Right. And the agents, but fundamentally, okay, so this is some nearest neighbor thing and whatever. Okay, update agents. So I suspect that there's a loop that has this kind of form, update agents all the time. Do you think that's a fair claim? So
yeah, right. And also probably there's a set of, there might be some set of primitives that are used a lot, like, for example, find all the other agents within radius X or something like that.
Right. But
many of them are also random, I assume. Many probably have a random element to them. Some of them don't, probably.
Right.
So I think that's two classes, probably.
Right. Okay. So there's, I think we can, I don't think it's going to matter much whether they have a random element. I think that that's just going to be a thing which doesn't depend on the environment. Each agent at each step, whatever a step is, looks at its environment and does something and updates itself. Do you think that's the typical pattern, or does it update another thing as well? Maybe it, and perhaps it spawns new agents. Do you think it affects other agents, or do you think it only looks at itself? It only affects itself?
I would say it should only affect itself. Right. And if there's some other code, if some other agent should be affected by the actions of this agent, then the other agent should just look at the state of this agent and figure out that it should do something.
Okay. So let's assume that the state.
There is a class of, I'm just trying to understand, actually. So I'm by asking questions. So there's a set of algorithms that are, for instance, used to compute optimization, to compute optimal values and run optimization, like genetic programming or various kinds of evolutionary algorithms or physics-based algorithms. Do you think that those are, that's how they work?
I don't think those are agent-based models. I think those are a different kind of model. I think that genetic programming is, okay, so my claim is, maybe I'm too steeped in the physics project, but genetic programming is a story of what we're calling branchial space. It doesn't matter where the things are. They don't care where they are. I mean, there are obviously versions of studying evolutionary biology that care where they are, but fundamentally in genetic programming, all that matters is you have this thing and it has this genome, and it's going to interact with this thing that has that genome. Whereas I think these agent-based models are more oftenly have a notion of space.
Well, but also, I mean, I think that I think like if you had a genetic programming angle to this, you'd probably do that like one level higher or something. Like you'd have all your agents doing their thing, and then you'd use genetic programming to determine, what parameters are the agents that you're spawning going to have.
Right.
Like that's probably the more common case. But for the physics stuff, right? I mean, I guess, I assume you're thinking about stuff like, n-body simulations where you have Newton's third law, like that kind of thing, right?
Yes. Okay. But by the way, we should add to the existing stuff. We have our n-body simulation function, which is, a fine example of something where we have.
Why do you think it's agent-based?
It's not agent-based. It's an example of a modeling framework.
Okay, fine.
It's like,
Yes, we agree.
Right.
Okay.
But it is sort of a little bit like agents, because look at this. I mean, this is kind of interesting, right? This representation that it uses of its state.
And also, I mean, you can write an n-body simulation as an agent-based model, right? There isn't, you can have just sort of self-contained code for each point, and a minus floating point error, everything will work.
Sure.
Right. So.
Okay, here's another question for you. So here's another example, whether you think it's agent-based or not. So when we modeled queuing networks, so first, it can be seen as a random process. Things like computer servers that get requests, or a doctor's office or an airport or something, a human-made system. They're literally agents coming through. Okay. And the way you need to simulate that's definitely a random element to it. Do you think that's an agent-based model?
I think that you could study it in an agent-based way, but queuing theory has advanced beyond that point. So it has kind of a more complete theory.
But it isn't, because once you get to real-world systems, you need to simulate it as basically, you need to simulate it. There's no analytics.
It's probably similar to this, yeah. I mean, I think the thing that we have to understand is I'm sorry, I'm just looking at this little thing. My gosh. Okay.
But the questions that Roger's posing, they're helpful. I mean, they help to motivate this idea of metamodeling itself, which we haven't necessarily completely described yet, at least in this live stream for other viewers. I mean, so part of the idea is that on the one hand, if you look at that list that's presented at the top, some of these are very fundamental models of computational behavior, such as cellular automata, right? Some of these models, however, especially in practice, are modeled by researchers who are, we can say, straying somewhat from completely fundamental study of computational behavior. And what we want to do with metamodeling is to establish a practice for extracting from these less computationally foundational models, simple underlying behavior. So with cellular automata, it's already highly simple. So we can run these CA programs and we can see what they do. But what Roger is asking is, well, with these other kinds, like with n-body systems or with queuing, et cetera, can we find underlying very simple rules or behavior models for describing these, and how do they relate? And it might be the case that with metamodeling, when you look in areas of mathematical sciences, or what's sometimes known as complex systems theory, but is often in practice much more applied, it might very well be the case that undergirding these, there are simple underlying models that actually have quite a bit in common. And that's really what we're looking for in the end with this.
Yeah, well, right. But I mean, more practically, at some level, what we would like to do is something where we can say, agent-based model of blah, 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 and where we can write voids in one line, for example. That would be an example of an objective here.
I think the basic thing is just that there's a whole class of these models that.
When you say that, you don't mean James Boyd.
No,
I mean BOIDs. Yeah, okay, that's very confusing.
Okay.
Okay, but I guess the point is just that, voids being one of them, especially in sort of the complex systems world, there are just endless agent-based models and things like that. And right now, there isn't really a super concise way of writing those.
Right.
I think this is a fairly
another good point.
restrictive, even a fairly restrictive version of this is already somewhat useful, just as basically something that's, in the same way that net logo is not that general, but still there's a whole big class of models that people use it to play around with. It's worth just supporting some of those.
Right. Okay, so let's understand what we would need to support those. Basically, in every agent, so we have the state of the system
Recording
is a list
in progress.
of agents, basically, with each agent having a certain state, an unordered list of agents, probably. Do you agree with that statement?
I agree, probably, yeah.
With each agent having a certain state. Okay, and for example, this state here is a pretty reasonable kind of state for it to have. So some of that state, some parts of the state are fixed, some can vary. But I don't see any particular reason to distinguish those two things, just as in the n-body case, the velocity and momentum vary, but typically the mass does not vary. Does that make sense? But then, now, what's interesting about the n-body case, and non-trivial, is that I think in a lot of these agent-based things, it's just you do a time step, the Boyds, the ants, whatever, look around, they do their thing, then they go to the next time step. In n-body simulation, that's been made more sophisticated because the time steps are adaptive and all kinds of things like this.
It would be very cool to support some kind of adaptive time step thing with at least some models, but
yeah,
I'm not sure how. It definitely would require the person implementing the model to do a bit more work, but I'm not sure how much more work.
Well, it may be that if we correctly parameterize the models, that we can figure out for them what kind of adaptation is possible. It may depend on, look, the fact is, if, okay, so I suspect the following is true. Assume we can compile the function that implements what each agent does. Okay, so I'm going to make the following outrageous claim. If we can do things like automatic differentiation on that function, we can figure out if we can do numerical analysis.
Well, but hold on. That's if it's a function like, the n-body function or something like that. But suppose it's, I don't know, suppose it's something where every, at every step it has a, 10% chance of picking a new target position or God knows what, something like that. Okay, then how are you going to implement that?
Well, that's an interesting one because that particular one, a 10% chance, that has to go from a discrete random process to a continuous random process. Maybe Roger can say something about that. But then what is the story of automatic differentiation in the presence of randomness, Roger?
Well, any numeric procedure, there's, I don't think I can answer that just that flexibly that you ask it. I think for a particular function, it's clear what it does. For a particular program.
No, but if you feed, okay, so here's the way to think about this. Think about stochastic calculus, okay?
Yeah, but I don't think stochastic, algorithmic differentiation cares if some variables are random or not. It just differentiates. It doesn't, the question is what's valid. What makes it sort of useful.
No, I understand
in terms of doing it, it's not a problem.
But my point is, let's say you have one of your control systems things. And by the way, control systems is another area of, all the control systems functionality. is another area. And it will be very nice as we think about these agent-based models. Just imagine you could put, a PID controller on your ant or something. Is that a reasonable thing? What would that look like, Roger? If let's say that the individual agents were responding according to a control system.
Well, you sort of do that with drone when you have big clusters of drones, and so there's sort of things that you call like distributed control systems. So if you want to control a whole, like a flock of drones, kind of like in the last Olympics or something, you want to, there's individual control for each one drone, which it then breaks down to even more individual control for the individual motors and stuff.
Right.
But then there's basically control for the whole flock to behave. And so that's kind of what, what's being worked on. How do you control that whole flock as one object, basically?
Right. But what I'm asking,
but the individual ones that they might only care about distances to their neighbors, for instance. That's to think, roughly speaking, how that works.
Okay, but so it is in fact, okay, so let's ask at the level of our software stack. Mm-hmm. We have a control systems, a whole bunch of control systems functionality.
Yeah.
If we wanted to insert that, okay, so in a rough approximation, okay, the rough workflow, approximate workflow for agent-based models would be, we have a global state. At each step, each agent's function ingests some aspects of the global state, some typically relative aspects of the global state. And resets its state. Correct?
Well, probably, I mean, probably in the most general case, you just want it so that each agent takes its state and some global state. I mean, maybe it's just that, it takes its state and then the states of all the other agents.
Although I suspect that a very common function will be the nearest neighbor agents or something.
Sure, but right. I mean, I think the most general case would probably be that it takes the global state, and then there are a whole bunch of other, like let me give you some examples, right? Even with Boids, right, which is one pretty simple model. I've seen Boids where you find all the neighbors within a radius, where you find the n nearest neighbors, where you have some sort of adaptive thing where you find the n nearest neighbors, but you are sort of sticky. So if one of them goes a bit further away, then you keep looking at it, stuff like this. I don't think we'll be able to parameterize all of those.
All right, fine. Although it might be that we end up with some kind of special function that's useful for those kinds of things. But you think it's a nearest, but might, include weird stickiness and things, weird historical stickiness.
Well, or any other things. Like, I mean, I don't know, if you look at, if you look at some of the more, like if you just think of Boids, it seems pretty clear cut. But some of these models, they don't even, the spatial aspect isn't as important and stuff like that. And it breaks down a lot. Or maybe where they just have a fixed set of 5 neighbors that they keep the entire time. So I don't know. I think that, probably you can have some spec that looks like the spec for nearest, which accepts, you could say all, and that would do all of them. You can give it a number and you can give it a radius. But
okay, so what we think is roughly there's an agent function which gets the current state of this agent and the global state and returns new agent state. Right. So
and
this is
also a global function, like if there's some, well, actually, because sometimes there's stuff like there's state in the background, like maybe it's a bunch of agents walking around in a field and there's properties of the field. So you might also want to have some like there's the agent state, then there's the other agents, like the neighboring agent state, and then there's the global like background state. And you might also want to have a function which updates the global background state every step.
Okay, so hold on a second. So it might want to distinguish a list of agent states from a global background state. I suspect that that's going to want to be hierarchical.
What do you mean?
Well,
Hierarchical?
rather than just saying that there's agents and there's a background. I mean, why couldn't there be super agents? There are little creatures that live inside bigger creatures and things like this.
I mean, because those, like, I think there's a fundamental distinction between, like, yes, you could implement the global background as like having a special agent. Agent number 12 is the background or something like that. Yeah. But it'll just be a total pain. And it's such a common idiom.
Okay, all right. Okay, so fair enough. So that's okay, but let's go then. Assume we have something like this. Okay, so then what would Boids roughly look like? What would the agent function for Boid? I mean, oh no, I was going to say something else.
What do Boids do? I mean, I've seen pictures of them. What do they actually do?
Boids? They go around in flocks.
The goal is to create a flock or something?
Yeah, right. So here, for example, let's do an example. I don't know if this is a 3D one. I don't know whether this is particularly useful, but I'm sure if we play this, absolutely nothing happens. There must be a 2D Boids thing here.
They flock around like birds or like fish.
Okay.
So there, I can explain where you're finding this. I mean, there are 3 rules for Boids. There's the cohesion, where basically the Boids will, a Boid will try and move toward the center of mass of all the Boids it sees. There's separation, which is if it's really close to another Boid, it'll move away from it. And there's alignment, which is it tries to, point in the same direction as the Boids that it can see.
Say that last one.
So the alignment is basically that they try and point in the same direction as the other Boids around them.
Okay.
Okay, so there they are, Roger. Okay, world size, starting max velocity.
And they basically have those 3 rules that you said?
Yeah, and that's it.
Okay. And then you can vary the strength between them. That's probably what the parameters do here.
Yes, yeah, you can vary the strength, and you can vary what other Boids each Boid can see, because normally they can see within some radius, so they can see the top 3 nearest or whatever.
I see. Okay.
Right, so here the number of Boids is too small and the radius is too big, so they can all be in one big flock. But if the radius is smaller compared to the number of Boids, then like the visibility radius, then it'll do funkier stuff.
Mm-hmm.
Somebody needs to fix this bug.
This stuff has actually been, I mean, I think that was introduced as a toy problem in the 80s, right? 1980s or something like that. The Boid business. Is that
It was introduced by a chap called Craig Reynolds, who was doing them for movies.
Was it the 1980s or?
Yes, in the 80s.
Okay. But in modern times, this stuff has become, quite studied, for real industrial things. Like you want one operator to control multiple drones.
By the way, I bet that this is a change in the numerical evaluator for, sorry, this is irrelevant, but we might as well report the bug.
I think arctan of 0, is just kind of ambiguous.
Well,
it's
I know
probably
that,
when there's a Boid that's off on its own, and so the center of mass of it's trying to figure out the angle it needs to point at in order to point at the center of mass of its neighbors, and it's
right.
It's 0.
Anyway, okay, sorry, Roger, you were saying.
I'm saying that sort of related problems have been very seriously studied by roboticists and others, control people, and so for instance, you want basically one pilot to control a whole group of drones.
Mm-hmm.
For instance.
I think there's a huge Boids industry, by the way. I mean, I don't think this is not a corner case.
So it's not I mean, this seems like a toy to me to illustrate something, but I'm just saying it's also, actually useful.
Well, I think there's a whole world of, I think you're kind of right, but there's this whole world, particularly in sort of the complex systems, orbit, there are endless agent-based models like this that, yes, are basically toys, but people do spend a whole lot of time, studying their behavior.
Right, because but the goal there is it's some kind of insight, right? It's enough to do this, and you get the phenomenon,
Right, but Roger, what you're pointing out is that there's an industrial use of these things, like and Intel's favorite, drone configuration, firework display type thing.
Yes, and I'm trying to remember. There are other related things, but drones are so very visible today. But they're these things where you can't necessarily communicate so well with everything that you need to control, like, I don't know, power systems, distributed power systems, and things like that.
Right. Right.
So
Okay.
So some of it is very, has gotten a lot of attention, and is actually seriously used, or getting
Indeed.
seriously.
Right. Okay, we have various comments on the live stream. I was just exchanged mail with Craig Reynolds recently. He's mostly working on camouflage models these days. And actually, I know Christopher had done some stuff on camouflage models too, and somebody should send said things. Okay, look at this. This is Craig's original page about Boyds.
And
those look
what,
like Cray computers there.
Yeah. Was that, what was it in the 80s? Was that roughly the right
Yes,
era?
yes. 86,
Okay.
he says.
Okay, cool.
And it was used first for some Batman movie, as I recall.
Right.
Okay. So anyway, so that's an example of a model. Being pointed to one other thing. Yeah, go ahead.
Yes, I mean, by the way, if you want to see examples of other things, I mean, just to get a sense of breadth, because I think that right now what we're talking about is very Boyd focused. I just sent in the chat a link to the NetLogo, example models page. So I don't know, if you pick something random, you'll probably see some weird model that looks fairly different from Boyd's. I think some of these aren't really agent-based, but just,
peppered moths.
They
seem similar.
Well, I think they're similar in the sense that you put the moths in different places, but
there's one that I like. I haven't really looked at many of these, but there's one called, I think, Rhodes or something.
But do they all have this spatial thing to them? I mean,
no.
Kind of.
Probably,
well,
maybe these
ones.
I mean, look at. So some of these turn into cellular automata. Some of them are actually cellular automata. But the whole point is to go away from cellular automata to something where you are, okay. So the simple-minded way of doing this is it's kind of like, something like a mobile automaton or a Turing machine or a 2D Turing machine is picking up a global state. But the whole point here is that there tend to be interactions between agents. But Christopher, what was the one you were suggesting?
Well, the one I was suggesting is called Rhodes, just because I know it has background state, although it looked like that termites one also had some sort of background global state.
There's also, I've never wrote this, but you could write your sort of robot to do to have tournaments between robots. They were, so each robot was an agent and it got to fight another agent, as opposed to flocking like we see here.
Yeah, and then you can do the genetic programming thing of,
So there are genetic. Okay.
Yeah.
Dining philosophers. Is that?
Oh, that's the one where they each want each other's utensils.
Indeed. But is that one is one where the timing matters?
Yeah.
Right?
Right. I mean, but now there's also some stuff like this where I imagine that, right, it's probably more natural just to write that from scratch than it is to use some agent-based modeling framework.
I agree, especially because that's one that specifically bites into the whole, synchronization issue. I mean, I'm sure something like this might be a reasonable, this looks like an Eden model. And I guess that's just an Eden model. Yeah. I mean, that's again.
There's another nearby thing, which I'm not, it could be this, but I don't think it is the same, which is sort of discrete event simulation.
Yes.
Which sort of fits the queuing network stuff that I was talking about, elevator systems, things like that, which you could argue that there are agents going into elevators and picking floors and stuff, like traffic systems. Is it this?
I don't know. I think it's a corner of this. I mean, look, another thing that's very directly, so aggregation models are see, that one is different because that one is sequential. That one is sequentialized. You know, like the Eden model. Remember that guy? Where you basically, let me see, I can find one.
What is Eden?
This
is, if I was a complex systems guy, I would know all this, right? Because I recognize the name.
I'm not certain you would actually. I'm not sure they even talk about this one, but
okay.
But this one is you've got a cluster, and you randomly, at every step, you randomly pick a point on the boundary of the cluster and add a new cell there.
Okay.
Okay.
And it goes to a disk, and it converges to a disk.
Well, almost a disk. It actually doesn't turn out to be exactly a disk on a standard square grid, and you can have slightly more elaborate rules. You can also do diffusion limited aggregation, where instead of just adding this at the outer boundary, just picking a place, you insist that the thing has to follow a random walk from infinity to get there. So that means that if there's that it's much less likely to get into a shielded region, so to speak, into a bay than it is to get onto a promontory. And so it has a habit of okay. So so this case is interesting because it is sequentialized. That is, you're adding one element at a time, which is a little different, I suspect, than these agent-based models, which are quite parallel. And my guess is that we will wind up with a different function that does essentially the aggregation type thing.
Right. I think that the basic, right. There's a very big set. If we look at, for example, again, the net logo models, there's a huge class of things they do. A lot of them are best done from scratch. And I think that, if we want to have some agent-based modeling function, it should really only try and get the ones that, right now are very easy to do in, say, net logo, but not very easy to do in Mathematica.
Right. Right. Well, so fine. So that's our target to begin with. Although I do think the aggregation model thing might actually be easier. So that would be, oh boy, we've already got a thing called aggregation layer, but let's imagine we have aggregation model, and then it's basically, you have to define well, you have the initial state, which is a grid of some kind, and you have the well,
I think this one is really from scratch. I'd be shocked if there was really much. This is a function like cellular automata, although it's probably more, stochastic. But I don't think this will be a very general function.
Right. But look, this is what it looked. No, well, probably you're right. But it looks at a neighborhood. So they're really cases, look at a local neighborhood. Well, basically it's what the heck is it? Yeah, it really depends on things like surfaces. Find a local neighborhood with a particular form. Find a local neighborhood with a particular form and do something to it. So, that would be things like a totalistic rule would just say, yeah, so I think what this is more like a sequentialized cellular automaton, where you're just looking at a randomized sequentialized cellular automaton. All right, so this is maybe irrelevant. But in terms of the, yeah, go ahead.
Well, I was just going to say, in terms of the agent-based, right, I think the things that we probably want to focus on more are, again, things like, Boids, or like those, termites or whatever other random models were there, where it's sort of like, I don't know. I think they have constructs like, okay, you want to know, if the background is a grid, which I don't know, maybe it isn't always, but if the background is a grid, what square am I on, or what's the, what color is the square I'm on? Or you might want to do something like point toward this other agent, or point toward this position, and then move forward this much. I don't know if we want to have that much, turtle art kind of stuff. Turtleology. Right, but I just think these are the kinds of primitives that are probably.
All right. Okay, let's go back down here. So we're basically going to go, turtle-like agents. So they typically have they might have a position and direction. How common is that?
I don't know. I mean, I think so. So one of the problems is that at least a lot of the things that, at least that I've seen in sort of the complex systems world, they're very influenced by the tools, in the sense that, there's a certain tendency to, have things running around on a 2D grid, with a colored background or whatever, because basically that's what NetLogo supports. So I think we should be more general, but
right.
That's in terms of existing stuff, that's very common.
Well, so the point is, one question is, does velocity, is there an x and an x dot, which there is in this case? Because the velocity implies something about the position. In other words, do the parameters have intrinsic interdependence? E.g., velocity and position.
I mean, maybe one more general question is just that it seems like we probably should support the most general case where, you don't necessarily have a direction. You might not even necessarily have a position. But then it would be nice if then we have special stuff for if you do happen to have a position. And so
All right. So what's the relationship between nest list and everything we're talking about? To what extent is agent function just a nest list? I mean, it is a specialization, I think, of nest list on the global state, I claim.
Well, where global state is both the background state and all the agent states or something.
Right. And I mean, init state and some number of steps. That will be a most minimal version without adaptive time stepping, without any of those kinds of things. But it also has one important feature that's a mess, which is that it's not going through and saying which agent you are, so to speak. It's just, it doesn't distinguish your local state. It doesn't have that. There's another loop here, which is basically saying, agent function is mapped onto, well, whatever the global state sub me, so to speak, and what is going on here. So, but basically, this is somehow if the global state is a list of associations representing, let's imagine that the basic data structure is a list of associations representing the states of agents. I mean, and do you think that's a reasonable thing to do?
Yes, except that I think that there probably does need to be a background, some sort of other information place.
Well, it's a bit like a sparse array then. I mean, should it be like a sparse array, or should this thing here have a wrapper that represents, where it says agents and then it says background?
Well, I don't know what you mean by sparse array. I mean, I just mean that, you have the states of all the agents, and then you also need the states for, the stage on which the agents are moving, and any other global metadata that all the agents need access to.
All right. Well, so, I mean, okay. So my question is, in terms of data structure, is the right thing a list of agent states and a background and an association, or should it work differently?
I mean, that seems reasonable, I guess. Yeah.
But then so I mean, this function, I'm just not sure it's worth doing it this way because, well, no, I mean, in the end, the output is going to be, as a function of time, the output of this function of the nest list, agent-based nest list, or agent-based. I mean, what we have for n-body simulation is we have the simulation function, right? Or we have something which is the output of the simulation. Is that making sense?
Is that what you imagine that this, so if you write, basically, if you provide state update functions, that simulation function can run the full simulation. And maybe provide some global final state, some something that you accumulate along the way, something that tells you how it evolved. Or what do
yes,
you want?
exactly. No, I think that's right, because it doesn't seem sensible to store, to just say explicitly, we're going to have a list of states here. Maybe you can get that out as a property of, basically this becomes agent-based simulation of blah, 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 blah. And you can say here, if you want to, you can say final state, or you can say something else. I think that's what we're doing in the case of n-body simulation right now.
Well, I think the main motivation for doing that with n-body simulation, which I don't know, maybe it turns out we'll support this here, but I think the main reason is because it's basically returning some kind of interpolating function.
Yes.
But if you really have clearly defined steps, I guess you can do the same thing. I'm just imagining, one case that might come up. I know, like in, I don't know, 10 years ago or something, when I was playing with Boids, I had these things where it was a problem if you you didn't want to store all the time steps because there'd be way too many, like eat up all your memory. So you'd want to do something like store every 100th time step.
Yes.
So I'd worry about, having some big object that, you run it, and then this object is massive, and then you're supposed to query that. I think you want to have some kinds of, you want to be able to request only certain things be stored even when you make the object.
Okay, so let's compare that with ND-solve and interpolate.
But sometimes, like for discrete event, for instance, simulation, which is also, one could argue is in some form of agent-based, but one of the things that there's usually something that is the goal with a simulation, something that you want to accumulate, the distribution of this or that. Then you might even want to optimize it. And so they have, there's sort of things that promote that workflow, like something that reduces the variance, for instance, so you get the value more quickly. That you're kind of looking at, you're stimulating.
Well, like with probabilistic programming, you want to be able to get the distribution without, one way to get, one objective, compute probability distributions, which after all we've done, where you could, e.g. Monte Carlo, but that isn't the best way to do it usually. But there may be better ways.
Yeah.
And I agree that that's a thing you might want to do independent of, and particularly you might want to do that if there is randomness in the simulation.
That's why I'm thinking it's useful to think about sort of what is the workflow and what's the goal, because like interpolating function that we deliver from numerical simulation, it makes all the workflows that work for other functions, like special functions, also work for numerical simulation. That's one of the things that does. It plugs in, so all the same workflows apply. Okay,
well, fine. So then the question here is, what are the relevant workflows?
What are all the things? And I think that for all these other simulation or modeling areas, we are going back and asking the question why again. Because we're expanding the workflows and we come to a little bit different conclusions on what's
okay. So one thing would be, and by the way, this in the Wolfram model simulation stuff, we have exactly the same issues over again. We can add that to our list up here. In fact, if we look at that very function, we can see
there's probably a whole set of models also that run on graphs as opposed to run on space.
Oh, that's a good point. That's a good point. Right. So
see, that's not hard to implement. If you have the background, if you have this background data, the background data could just be the network. And then
what is the base space is the question.
But what is your goal, like in animation? Is the goal graphics?
Oh, yeah,
right.
Okay.
I think that the ultimate goal is you just want to know, what you want to know the output of nest list, basically, just what was the sequence of states. But it might be nice if we have nice graphics in certain cases. And if for example, all of the agents have a position position argument, then maybe we can have a little graphic for it. I don't know.
Well, but here's an example. This is,
or is it to compute some statistics, some, do those agent in fact compute something?
right. So I mean, it might be generate final state, e.g., to plot it. It might be show the paths of a few chosen agents through time. It might be find the distribution of densities of agents in a given region, let's say.
Let's say, I think for stuff like that, if you want to do statistics on the whole time series, that's very easy to do just from scratch, right? If you're just given, here are all the states, it's easy to just pull out all the positions and.
I know, but if that's the right way to do it, but if we had some ability to do, some kind of generalized, I mean, this is sort of important sampling in, well, multi-way graphs in our modern way of thinking about it. But I mean, in, something like probabilistic programming, where you're ending up doing important sampling in the paths of all possible program, possible program paths, you might do a hell of a lot better than just saying, generate the giant, every time step, every branch, so to speak, thing. Right? In other words, there's a lot more information. If you look at, to put it in physics terms, the multi-way graph, right, where you're looking at the branching, you say, if I take this probabilistic variable to this value at this step versus this value, I've shared a lot of other state, right? Whereas if I just do pure Monte Carlo and I've got every state generated afresh, I've got huge amounts more data to get the same amount of information. If that made sense. Maybe that didn't make sense. But okay, so I mean, what other things? I mean, so basically what we want is some kind of, agent-based model, agent-based simulation function or something like that we can query various features of. And presumably, when we do the simulation, we want to be able to give a time stepping information, like the Boyd's thing, where you say do 100 steps between every one that's stored, presumably. Question: in the usual way this is done, it is the case that the sort of distributed computing aspect is done in a trivial way. That is, you have a single time step, and it's like every Boyd look at every agent, look at all the other agents and see what to do, synchronously, so to speak. It's not ripple through the agents, updating one first, then the next, but depending on. In other words, it's. I believe in signal processing, that will be the difference between finite impulse response and infinite impulse response. Did that make sense?
Actually, I was going to bring that one up earlier because, for example, I think it varies. Like, for example, with Boyd's, you usually do, everyone moves at once. But for example, with the traffic modeling stuff that, like solutions, a little while ago, that was not like that. That was one car moves first, then the next, then the next.
That's interesting.
I mean, because the thing is, like with the cars, you have requirements like if one car moves one way, you have to make sure the next car doesn't move into it. So there's actually, it's not local. The model is not local.
Right. Well, what about? I think that's why doesn't the same thing happen with birds?
Or do you don't care as much if they crash into each other? I mean, I think you just don't really care as much because it's not discrete and you have continuous space usually. But I mean, I think that's something where it'd probably be worth having an option or something where you can kind of specify.
By the way, that is the exact same thing that we're running into in this multi-computation business about evaluation fronts. That's the same story of evaluation fronts versus tree traversal order. They're all the same, same story, I think. I mean, this is essentially is it breadth first? Is it depth first? What is it?
Well, it's much simpler though, because I think that, I mean, okay, maybe this isn't, I've never seen a model like this, and I haven't seen that many, but I've never seen a model like this where you run, one agent twice before you run another agent, right? Like, I mean, I think that,
okay, so one example
all you care about is
in n-body simulation, a random thing that's become very famous that I suggested to some people at lunch in sometime in the 1980s, that some n log n algorithm for doing n-body simulation, where you basically where you clump things together and consider, I mean, I guess that's a little different, where you consider, where you have hierarchicalized the structure of the simulation. I mean, that's
Barnes hut, right?
Yes, right, yes.
I think that's probably too custom. Like, I think that's something that, yeah, I mean, the actual implementation of like the Barnes hut algorithm is sufficiently, I don't think that it would be possible to do that in sort of in a framework like this.
But I think that what it is, it's hierarchical. That general idea of, I mean, okay, it probably depends on the fact that it's gravity, which is a long range.
It does a lot. I mean, I can tell you basically. I mean, it works by you construct a quad tree, and then you basically traverse down the quad tree, and for each sort of point, for each self-gravitating point, it goes down the quad tree on all the different branches, and it will stop going down once either it reaches a single point, or once the sort of square of that quad tree is, the size of the square divided by the distance away is less than some number. Right. Which I mean, yeah.
The basic point is, do you represent the complete state, or do you represent it as a quad tree?
But see, I don't really know of any other, like, the quad tree, that whole setup seems.
I agree. It's mostly long-range forces. It's probably mostly relevant for long-range forces.
But the quad tree is the complete state. It's just sort of organized for fast search.
Exactly, but it's organized so that many effects don't require you to go to the bottom of the quad tree. I mean, it's similar to wavelet type stuff, where many things you compute don't require you to go down to the individual bits.
But see, this is only specific to these n-squared things anyway, right? Because if you're running something like Boids is not n-squared, because there's they have a limited visibility radius, and so something like this I don't think really makes any sense.
Fair enough. Okay, probably too specific. Okay, a comment. I see there are multiple comments on our live stream. All kinds of interesting things here, including swarms of robot vacuum cleaners. Yes, mixing Boids with neural nets to evolve a battle Boid. Yes, people have done that. Oh yeah, Stove is commenting on aggregation models where there's a chance to detach as well. That's interesting. Yes, we haven't thought about that. Okay. Michael here is saying, need a generalized framework for agent-based simulation and machine learning where internal states are abstracted like a gradient policy optimize. Roger, can you unpack that? Or
no, I don't know what that means.
I mean, I know those words. I just don't.
I do too, but there's some. This sounds like it's some.
Well, I mean, the main issue is. Okay, so one point is, okay, look, I mean, things in the loop that might be interesting. Our control systems framework, machine learning, system modeler stuff. What else might be interesting to have in the loop, so to speak, for an agent-based model?
Visualization stuff.
No, but I'm saying in the loop as part of the action of the agents. I mean, like you can imagine the action of the agent is a PID controller, or the action of the agent is a neural net.
Sure. Okay. Sure. I mean, certainly there are a bunch of functions that will probably be very common, like nearest maybe, but.
Yes.
Yeah.
Right. But I mean, many of these. So again, I was asking Roger for control systems.
Yeah.
Okay. Is it the case, like with machine learning, I can kind of imagine what it would look like. It would say predict, blah, 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 current state. And then it would return what to do.
Well, I mean, I don't think you probably want to use a predictor function that you'd use in each agent, but actually this does raise the question of this would definitely need to interact with reinforcement learning stuff.
Yes, that's quite true.
I haven't really used the reinforcement learning functions enough to know whether or not that's,
reinforcement learning is a mess. And as Roger keeps on emphasizing, it's the same story as control systems.
As optimal control, yeah.
Right, but I mean, for example, if the way, I mean, again, I don't really know those functions work right now, but if those functions worked in some way where it's like, oh, you have your, reinforcement learning object, and then you can call some function in each agent and it will add to this object, then that would probably be not too hard. But if you need to, my impression is that's not how it works. It's more of a, you have to give it a like.
But all controllers, I mean, except for the very simplest ones, they have their own state too. They have sort of the state on the system they control, and they have their own state. And given those two states, they compute what to do, so to speak, their action.
Okay, so
that's the basic.
What is this? I mean, this is an example based on an external thing, but
this is usually the example in the control theory 101. This is usually the first example shown.
Right.
But the point is that agent-based models, that's an external reinforcement learning environment. I think agent-based models would be another, environment in which you want to do agent-based reinforcement learning. But I think it's these reinforcement learning environments. My impression is they're much more one-off.
They're a horrible mess. I mean, we've tried to do the same metamodeling thing for those, and it's super. This is the thing we learn in doing this design over and over again. Every time the minimal example of something is complicated, the level of usage is dramatically reduced. And so
I think that this is the problem with those reinforcement learning environments is that people want to do something like, I want to do reinforcement learning in, Super Mario or something like that. Right. And so that's, of course, the environment is very complicated. But I think that you could definitely imagine having much simpler examples where you have, where your boids are learning to, avoid the predator boids and stuff like that.
Yes. Yeah, well, that might help. I mean, that might be a case where it might help us to understand how to do reinforcement, because, what we have right now, I don't even know why that isn't here.
Can you only do reinforcement learning right now in one of these device open reinforcement learning environments?
You can do it in I don't understand where is the active classification? Why isn't that listed in anywhere in that neural net? Maybe that's
that was neural network layers, but
it was that was why it wasn't listed. Okay, so this is an example of the kind of thing we're dealing with. This is a mess. It's one of those functions that has. Okay, so Roger, optimal control. What's the function for that?
We don't have it. I mean, we have it in more specialized cases, but I think the promise of reinforcement learning is because it becomes super complicated in the general case. So we have more specialized cases like LQ regulator and things like that. But in the general case, optimal control has a curse of dimensionality, so you can't really do it in practice. So you need to approximate it. And what reinforcement learning kind of gives us is a means of approximation. Okay. So I think it's sort of promising in that sense.
Okay, so what the heck is this? I mean, this is the place where I just completely lose it, because like what goes in, what comes out, this is a very complicated setup. And at least when represented in terms of functions with arguments and things.
Well, it's dynamic. That's the problem. The function is not dynamic.
But notice that we've got the same problem over here. Our agents want to dynamically respond to their environment.
Yes, but well, I mean, the X that comes out there is the state of the system. Okay. that this in the first case there, I know the state of the system, and the only thing I'm going to do is to basically dot that state with something to decide how I'm going to affect the system.
Okay, but coming back to what we were talking about before, the fundamental structure is there is a function, it is applied. Okay, so just a minute, the sort of fundamental agent-based structure is there is a micro-step function which basically does, given an instantaneous state, compute the next one. Then there is presumably a evolution representation function that might aggregate many microsteps for everything it stores. So that's a fair characterization. And then out of that, we can extract. And so,
whoops, I'm in trouble. I got to go.
Okay.
Sorry.
So I mean, maybe the model is to be more like, I don't know, there are functions like cellular automata, or I think Turing machine now too, where it takes a big association and basically, there are different ways of specifying things and, or not specifying things, and it will, so one example of where I think that would be useful is, we talked about earlier, you could, your step function, it might be able to accept like the delta t, like how long was this time step if it's doing adaptive sampling, although I'm not sure exactly how that would work, or maybe it just always assumes that it's, time, the steps are all the same size. So you could have two different keys, for representing that. I don't know.
I don't understand why at the lowest level, Boids could be an n-body simulation. I mean, the birds could be falling out of the sky in parabolas and things, so to speak. In principle, one could wrap n-body simulation as the steps.
Sure. I mean, I guess are you making a statement about adaptive sampling or no?
I don't know yes, I'm making a statement that really, okay, we could have n-body simulation.
So I think one of the big differences between n-body simulation and this is that n-body simulation, no matter what you put into it, it always can go into ND solve, right? Which can do adaptive sampling. It can do, it's differentiable, etc.
Well, except for the when event.
For
when event is discrete.
Sure.
So I mean, in principle,
the point is that the general stuff you have in these agent-based models is like so far away from something you put into ND solve.
Well,
not all of them, which is, why I'm saying it might be worth basically having, if you set up the input in a certain way, it'll try and convert it into some nice ND solve thing with fancy adaptive sampling and so on.
Right.
But, there's also has to be, a simpler fallback case, which is probably most models where
I agree.
Doesn't do that.
I agree. I mean, the thing is, System Modeler is a good example of where you might think you can't actually do things with differential equations, but actually, even with 50,000 differential equations, you can actually do stuff.
Right. But I think the point is, though, is that you have to, if you want, for example, to support adaptive sampling, you need to provide more, So I think that in the simplest cases, basically you need to be able to specify, hey, I'm going to give you a function that can take all these special parameters, and as a gift for me providing such a fancy function, you'll give me automatic adaptive sampling, etc.
Yes, fair point. Yes, I see. Okay, so then, adaptive sampling, if you specify very particular functions, if you specify particular update functions in a particular way.
I guess, yeah.
Like you're suggesting in the cellular automaton case, you can either give an arbitrary Boolean function, or you can give something which has been parameterized where it knows a lot more. But I want to come back to the original question of, the original thing that you might do is you might have something where you say agent-based model, for example, or agent-based well, it would be n-body
I think simulation is better.
Right, agent-based simulation.
It's not a model, it's a simulation of a model.
Yeah, right, exactly. And so this should be modeled on n-body simulation, probably. And n-body simulation basically takes, okay, so it has the law, which is otherwise known as the rule, and it has a bunch of states of the bodies. Right? It's actually very directly analogous. Right? And actually, this is a nice feature because the bodies can have names here. Right? So, right, it either has a list of bodies or it has named, the bird called Fred and the bird called Jemima or whatever. I think that was the name of puddle duck, but that may have been in a very ancient part of history. Anyway, so this is the basic structure then. And then what should be returned, it should look very much like this, I would think. Does that seem correct?
No, I mean, I think that seems good. I mean, I think that part is pretty clear. The harder part is I think that the basic question is, what is the actual interface of what things do you need to provide in order to specify the model?
But by the way, even this isn't totally clear. So I mean, a typical, e.g., ants in a field or something, or in a field, the states would be, position, arrow, whatever. So it's going to look something like this. It's going to be position, arrow. I mean, just to be explicit about what will happen, it'll look like this, and it'll have a giant list of position, arrow, blah, position, arrow, blah. Okay.
And again, probably also you need to specify the background.
Yes, I understand.
Optionally.
Yeah, right. Okay. All right. Okay. So then it would be agent-based model of agent function, init, steps, and then it's some kind of, but the background can get updated as well, can't it?
Yes. Right. I mean, I think that you need the background. Also, you need like a global, you need some function. Like this is, I mean, probably for the rule, right? For the agent function, you're probably not just giving the agent function. I mean, in the simplest case, the first usage line, it probably is agent function. But for all the other ones, it's probably a big association with, here's the initial, here's maybe the initial background state, or here's the background update function, and etc. Right.
Okay. So what you're suggesting is that init normally would be could be either just a regular init, or it could be agent states, and then it's a list of agent states, background state or global state.
I mean, you could maybe even imagine, well, this is probably a bad idea. You could maybe imagine making it super general, where you'd have an association that says agents. You have an association where you'd say agents arrow this, and then maybe background arrow that, and then in the function, like in the rule part, in that association, maybe you could just say, I don't know, you'd say something like functions arrow, and then you'd say agent arrow this, background arrow that. I mean, the point being just that in addition to agents and background, you could have arbitrary keys, but I don't know how useful that is.
Yes. Possibility of arbitrary keys in addition to just agent state and background. Okay, but so roughly, I mean, one thing I'm thinking about is, once you've got this, okay, what is the minimal piece of code to make a picture? And essentially what you've got to do is you've got to say, I mean, it's a little bit of a mess, right? Because the list of these are, I mean, you would say, hash position /at.
Well, I think probably the most minimal, I mean, honestly, if all the agents have a position parameter and they're all the same dimension and so on, I mean, I'd imagine that the whatever it's called, agent-based simulation output or something, should probably just show it.
Yeah, okay, fair enough. Okay, so then basic visualization could just be a property of agent-based simulation data, which would be the analogous thing to n-body simulation.
And presumably you'd also, yeah, I mean, you could ask for stuff probably like the video of it, like the animated image, or you could ask for the,
video. That's nice, by the way. The fact that we have video now and you could just straight ask for that, that's a pretty nifty thing. Arguably, we should have that for n-body simulation as well. That's a good idea. Do we have anybody? Let me make that suggestion to Shadi. I wonder whether there are other functions like that that should have a direct to video. Huh, that's a new meaning for direct to video. A direct to video function, so to speak. Anyway, okay, so that's for some visualization. Or one could have, final state. Well, there would be other final state plot, those kinds of things. I suspect we're going to need a special function called agent-based simulation plot or something, because I think it's going to have lots of options, like how to render this particular attribute, in color, et cetera, et cetera, et cetera, and whether to make a bubble chart where the alpha bird is bigger or something, those kinds of things. Maybe that's too specialized. We should probably wrap up soon for now, but I think we're off and running on a quite interesting direction here. I mean, this looks to me like it's something that can be done. It's just a question of making sure that the, and then probably we'll actually want, special functions. And I wonder whether we actually want something where we say agent-based model voids, comma, some parameters. I mean, we could do that if it turns out, just like axiomatic theory, you can type in the axiom system every time, but it's a nuisance. And if there are, if there are a limited set of these kinds of models that we have to enumerate, that might be a good way to do it. What do you think?
Yeah, I mean, I think no reason not to. Yeah.
I mean, but is there a discrete set? It seems like there is. It seems like there's Boids and termites and this and that and the other. There's a limited number of these things that are.
I mean, I'm not sure how many really celebrity ones there are, like Boids.
Mm-hmm.
I mean, but at some level, if there are only two, that's still okay. I mean, it kind of makes it easier at some level.
Yeah, well, it's still useful. And I mean, rather than having a function specifically for that.
Right.
Okay, let's just look at a few comments on our live stream and then we should wrap up soon. Okay, Ali is saying the agent-based model can extend to computation done on meshes where a vertex and its neighborhood are important and abstract properties can be defined. Oh, that's a good base space question, right? So this is a good point. Base spaces. Okay, what are some reasonable base spaces? A grid or array? That's one kind of base space. A graph is another kind of base space.
Well, in addition to grid array, I mean, there's also continuous, like Euclidean space, which is maybe different from discrete.
Yes, I agree with that.
On a grid.
Yeah, right. Euclidean space. I mean, just to be exotic, we'll also, non-Euclidean space, spheres, etc.
I mean, spheres are reasonable, but hyperbolic voids, it would be interesting, but maybe not super necessary.
Not a V1 feature, but meshes probably is a real thing. Certainly a base space with a region is highly relevant. Oh yeah, here's another issue, is boundaries.
Right, if you have some weirdly shaped boundary region, yeah.
Boundaries.
I mean, this is why I think it's worth having some, right. I mean, if we're imagining sort of a spatial agent-based model like Boyd's, and you want to write it in such a way that, well, also there's stuff like, so that, okay, you want to write it in such a way that, for example, boundary conditions are respected. So you can specify that this one's on a torus, this one's on a sphere, and maybe even so that, they stay within some weirdly shaped region. I think you need to have other hooks in terms of moving them around and stuff like that. Or maybe you don't. Maybe you just update their positions as normal, and based on some options in the when you call the simulation function, it will sort of alter the positions to make them go around the torus or whatever.
Look, we've got incredibly elaborate boundary specifications for PDEs. We should just use them here.
Sure.
It'd be possible to use the same things, and e.g. velocity, does velocity, does it bounce from a boundary? Does it, is it, all those kinds of issues?
Yeah. But so I think those things are probably, again, I think this is probably that the right thing is just that, if your agents happen to use special magic keys like position and velocity,
yes.
and you've set, certain options, either as options or as something as part of the rule or as something as part of the kind of initial state specification. If you specify that, oh, by the way, I'm running on a torus, then it should just sort of magically update those magic parameters.
Right. So the basic point is, for position and velocity, etc., allow it to work like physical space. Make it easy to work like physical space.
Well, by that you mean stuff like boundary conditions.
Yeah, but also, well, I was thinking of, yes, I guess stuff like boundary conditions. But the point is that you could imagine something else, which is a Euclidean thing, but it isn't actually physical position. And I think that's an exotic case. I think the only case where people actually want physical like stuff, like velocity turns into position and so on, is, well, that's not even right. That's not even right. There's internal degrees of freedom that you can imagine, like spinning turtles and things, where, well, that's pretty exotic. Okay. Wave is commenting that someone has been doing tutorials on every single Boyd behavior. That's interesting. We'll look those up. Nested systems. Okay, that's interesting. Have to look that up. And James, maybe you could make some notes on these items. Yes, okay. Great. Standalone applications that run performance shader rendered Boyds. We have got a lot of stuff to do with shaders now. I mean, if you want realistic birds, I think we can make fairly realistic birds at this point. Although I don't think we can do, if there's some neat hack for having the Boyds interact with not doing all the ray tracing again. We certainly don't have any of that stuff. Okay, Ali is commenting on and off lattice. Yes, that's the point made here, on and off lattice simulations. Okay. Let's see. Okay. Ethan is complaining about lack of reinforcement learning. That, as I've been saying here, that was more a design problem than an implementation issue. Just because the things we ended up with in designs were just so unbelievably complicated, we didn't believe that anybody would be able to use them. And we have a few specific examples, but that's about it. And I'd love to get suggestions about how to do better design for this. And yeah, active classification is a function that people don't use. And is that because of bad design or bad implementation? I don't really know. comments about generative design. Boy, yeah, generative design is something which seems to, I mean, I'm very big on that kind of thing from cellular automata and other such things. And, it keeps on going up and coming down again. And I'd love to, I see these demos occasionally where people show, oh, we made these with genetic algorithms and it's a wonderfully shaped new way of making a can opener or something. But I keep on seeing these demos, but I don't know whether maybe this is happening in the world of CAD programs. I think we lost Roger, who might have comments on that. Let's see. Yeah, Marco is commenting a generalized simulation plot. We actually have system model plot, which is something that needs to, I agree that this needs to, where did I have this? This is compare system model plot, because system model plot has a lot of ways to hook into. That might be a good model for that. Because it has all sorts of defaults and so on and so on and so on for making the default plot of the simulation in this case. Let's see. Hold on one second. Okay, let's see. So flexibility, Ethan says, do you want to have flexibility in specifying the goals to optimize for? Yeah, I see. This is the policy. This is policy optimization. This is what the kind of thing Roger was talking about with swarm control and so on. What did he call it? Distributed control systems. Yeah, it's complicated. Let's see. Yeah, this is, yeah, Ethan is commenting we should have our machine learning people here. Yeah, we didn't think this was going to go in a machine learning direction. Okay, repast framework. Okay, you should look at that. I never heard of it. That's what I like about these live streams, as we learn about all these different ideas. Okay, never heard of this. Thanks. People don't use this to model things. They want to generate novel and optimal strategies. I see. Okay, fair point. As in a search for given this, I mean, but you have to have a model for the system, right? You have to have an environment that you're modeling, otherwise there's nothing to optimize. Okay, Nick is commenting that what is there to design? RL environment, RL model, RL train, done. Okay, prove it. I mean, if that's the case, wonderful. That, that wasn't what yeah, and Ethan is commenting that a core problem is that NetTrain doesn't support multiple ports within encoders. Yeah, I mean, this is, yes, the whole redoing of this framework to generalize it is something under steam. Okay, Wave is commenting. Okay, there's a lot of good suggestions here about generative. Well, generative art is a little different than generative CAD design and so on, I think. And I'm aware of many of the things you mentioned, but not all of them. Yeah, well, I'm glad it's alive and well, because we have been involved in this for a long, long time, from such distinguished things as the famous famous things like this, and many other efforts in generative visual design. Yes. Right. Well, we should probably wrap up for now for here. but thank you all for those suggestions, and we will continue at another time and try and nail this down a little bit more. So thanks everyone, and